Bismillahirrahmanirrahim. Assalamu alaikum. Yes, hello, hi everyone. So this is Process Modeling and Simulation CHENG324. Myself, Dr. Bassam Hamad. And today we are going to be taking a lecture about types of inputs. Today is the lecture number 16, and we will try to cover the types of inputs. And types of inputs is going to be within chapter number 4. So chapter number 4 talks about types of inputs. I already talked about types of inputs. I don't know if you can remember when I said about Laplace. I said that we do make sure that we have Laplace in our tables. We include those that are very familiar, or those inputs that are being used or do appear within our industry. So we mentioned impulse input. And this impulse input was like a Dirac function, and if you take that in the S domain, it was 1. And we talked about the step input, and step input is like you're opening a valve from a certain position to another position. So you're opening it with a certain position of M. That means for example from 20 to 30% is 10. Okay, so 30 minus 20 is 10. So in the S domain is going to be M over S. And we also talked about the ramp input, like opening something in a continuous way of opening it. So you're opening it every 1 second, you're opening 1%, another 1 second you're opening 1%, another 1 second you're opening 1%. You're continuously opening. So it's not like a step input which looks like that. Mainly it looks something like that, increasing. And this is represented as A T. Because it looks like a straight line, and in the S domain is A over S squared. And then we have the sinusoidal input, and the sinusoidal input is something like A sine omega t, and this will appear like A over S squared plus omega squared. Okay, so these are the types of inputs that we said that we are going to cover here. And if you just look at it, so any step input of a sudden change, so a sudden change in a process variable can be approximated by a step change of magnitude m. Okay, so what this equation means, that means it changed from a certain position to a new position. Okay, certain position to a new position, that means it was a certain position moved to a new position. So if I'm talking about a valve, so it moved, for example, from 20% to 30% opening. So what was the value of m? Here the value of m will be 30 minus 20, it will be 10. Okay, or 10%, whatever you call it, with the unit that is defined there. So it is equal to 10. And we can show this 10. I know it's written 20 to 30%, and that is 10. We can represent that as if it changed from 0 to 10. If we put our opening of the valve here, opening of the valve, for example, Fi prime, so you put it in deviation format. If it's not in deviation format, just Fi, then it's going to be 20 to 30%. Good? Very good. And if we stay in the problem, a very special case, it is just something that we bring in problems to make your life easier in the exam. Okay, so if we say a unit step change, so what does that mean? It means a step change, and when it says unit, it just means what? It just means that it is equal to 1. Okay, so my m is equal to 1. So if my m is equal to 1, then in the Laplace domain is going to be 1 over s. Great. An example of a step change other than the example I had just mentioned: a reactor feed tube is suddenly switched from one supply to another, causing sudden change in the feed concentration or the flow. The example I said here was the flow. However, you also can have a step input within the concentration. Okay, and that's an example of what we have. Another example: the heat input to a stir tank heating system in chapter 2 is suddenly changed from 8,000 to 10,000. So if the heat is changed from 8,000 to 10,000 kilocalories per hour, so what is the m? Yes, it is 10,000 minus 8,000 is equal to 2,000. So my m in this case, my m is equal to 10,000 minus 8,000 is equal to 2,000. And if you want to take the Laplace of that, this will be 2,000 divided by s. Okay, so what is your steady state value? Your Q steady state value was that. Your Q steady state value was 8,000. Okay, and this is another representation of the steady state value. I usually write QSS steady state, and some of the books they put a bar. Okay, they just put a bar here. So I'm just saying that you put a bar here. So whatever you like, but I usually use steady state value. Okay, so what do we have here? The steady state value. So it changed to what? To a new value. To a new value of Q. So Q minus QSS, which is Q prime, right? Which is Q prime. And that is part of the deviation thing. However, now we want to calculate what was the m. M is 2,000. M is 2,000 in that case. And what you see here, just not to get confused of what is going on here, what is going on here in this equation is something like that. I will show that to you. So Q prime is equal to Q minus Q steady state, right? So that is equal to 10,000 minus 8,000. Okay, so this is what it is saying simply. So that is my Q prime, and that is equal to 2,000. That it is equal to 2,000. And as you can see, that is written here 2,000. Then what is S of t? S of t just tells you at what time it is happening, and it means nothing in the equation. So if you remove it from the equation, it just means that it is out of the equation. And just not to confuse yourself. But we may use this. We may use this at some time when we start introducing many step inputs. So we introduce, for example, if I just put this example here, I'm introducing a step input and then another step input and another step input. So the other step inputs that I'm introducing from one point to another point, or from one point to another point, what I have here, I do have step inputs from one point to another point at a different time, And because they are at a different time, and this is at a different time, how do I appear this? I appear it by putting s as a function of t. Okay, so this just means that at what time it is happening, and then that's for the step input. And for the ramp input, again, we said that you're going from one position to another, and we have already given this previously. And the ramp input tells you that it was 0. Zero in the sense as a deviation format, right? So there's no change, and suddenly there was a change. However, it was in a ramp manner, and we call this ramp 80 in the time domain, and of course this would be a over s squared if it was in the s domain. Okay, so that is what we are trying to say here, a ramp as stamp to a new value. So it goes to a new value wherever you're going to stop. And examples for that, for example, field composition, it could have some kind of a ramp input, but in more clear examples is a heat exchanger fouling could cause some kind of a ramp input. Catalyst activity, it will take some kind of a ramp, but that is for some time. And ambient temperature, and that also takes some time. So it depends. It depends what are the cases that we could have a ramp input. Okay, what about a rectangular pulse? Rectangular pulse, we already have taken that before as well, where we said that in a rectangular pulse we have a step input. That's one step input. And then we do have another step input. So we have a step input from 0 to h. And actually, I would prefer here, instead of saying h, I'll put m, that term that you have in your head. We are just putting h here just to tell you that it is different, it is a pulse. But actually, it is the same. It goes from 0 to m, which is m over s. We see, it's m over s in the time domain. And actually, if we want to put that in the s domain, in the time domain, that will be m. M that happens where? That happens at time is equal to 0, s of t, and this is at equal to 0. And some other time at tw, So m is happening again, but it's happening at some other time of t minus tw. Okay, and in some books they don't use s, by the way, they use sometimes u. So you may find another book they use u, something like that, u t minus tw. And m is just a number. If you don't want to confuse yourself, so you're saying that this is, for example, as my previous example, from 20 to 30, so that will be 10. And if you don't consider u and u, if you don't consider them, it could be a problem. Why? Because you're going to say 10, I open 20 to 30, and then I return 20 to 30. This is equal to 0. And that is nonsense, right? It cannot be 0. It's like it's saying that I just went up and down at the same time. I did not go up and down at the same time. I opened for some time, and then I went down for some other time. So I went up for some time, and then I went down for the other time. Okay? So what do I have here? I have 10 u of t, 10 u of t minus 10 u t minus tw. And if I say this tw was after 5 seconds, for example, so this will be like t minus 5. Okay, how is this represented in the S domain? This is represented in the S domain as 10 over S. This is a number, so to be 10 over S minus 10 over S. And we said that we will use the delay idea. It's like there was a delay of the action. This step did not start from 0. It started after some time, after 5 seconds. And the way how we represent that after 5 seconds is like that in the S domain. And of course, this is equal to, now instead of saying 10, I'll say m again. So this will be m over s, common factor into 1 minus, and instead of saying 5 seconds, I'll say tw, okay, s. So I just put it in the generic format. Okay, and this example could be like a reactor feed is shut off for 1 hour. So you shut off the reactor and then you put it on again. So this could happen. Or fuel gas supply to a furnace is being interrupted. For some time that it was interrupted, there was no fuel gas, and then it was back to normal. So that it's like it went out of its normal condition, its normal position. It went up, and then it just went back to its normal condition later. Okay, so what did I say? I said that we could have a step input, or we could have a ramp input, or we could have a pulse input. In the first case, that will be m over s. In the second case, it's going to be a over s squared. And I'm just putting different notations, m and a, just not to confuse between them. And the third one will be something like that, which is h over s. Again, it's the same as m, and it's just a different term for you to look at. And that is h over s, or m over s, into 1 minus e to the power tws. Okay, so these are the equations that we have as an inputs. So these are the inputs. What else inputs do we have? We have an input which could look at like as a sine wave, and we already also discussed that. And as a sine wave in the time domain, if you just go to Laplace tables, you're going to find that this is just taking the a outside of the term, and this is like s squared plus omega squared, right? S squared plus omega squared. And we already gave you the idea that this shows that there's a complex root. And if you know that there's a complex root, if you want to go back to the time domain, you can look at this transfer function and know that it is a sine wave. Okay, so you will have an idea that this is a sine wave. Okay, great. One more input, we also mentioned that last time. If we have a Dirac function, and of course the Dirac function, if you take the Laplace of that, the Laplace of a Dirac function will be 1. If you take the Laplace, it will be 1. I forgot to say an example for a sinusoidal input. So an example for sinusoidal input could be 20-hour variations in cooling water temperature. So you're just testing and taking cooling water temperature up and down, doing some kind of a variation for a certain reason. So that is some kind of an example. But as I said, this is not very common in industries. And if you go to the impulse input, what is an example of an impulse input? Which is a short transient disturbance. So it's a disturbance like that. And that could be a noise spike in a thermocouple reading. Thermocouple depends on a difference in the voltage because of the different materials that we are using. And because of that, the thermocouple could have a noise spike because of the voltage thing, electrical noise. So that is like a spike. So something like that, spike, and it went like that. So this spike could cause a reading also in the temperature with this spike. Injection of a tracer dye. So you're injecting a tracer dye in a body so that it traces. So this is like this injection to your body, or a tracer dye to any other place. It is like for some time, and then it will leave the body. Okay, so you can track it for some time, and so on. So these are some examples for an impulse input. Now, we want to take the examples that we have and apply it to our systems. All what we have gained so far, and now I'm just going to go out of this slide. So what did we have so far? What did we have so far now? So we have that we can write here the types of inputs. Okay, the types of inputs, and the types of inputs that I have here. Okay, the types of inputs. Sorry for that. So going to the types of inputs. So we said the types of inputs that we could have, very popular in our industries, could be an impulse input, and that would be something that looks like that, and in the S domain is going to be 1. Okay, for a step input, f of t is going to be at, and the S domain, this is going to be a over s squared. For a ramp input, okay, so for a ramp input, I'm going to have f of t is equal to oh my god, what did I do? For a step input, this will be m, and that will be m over s. For a ramp input, it will be at, and that will be a over s squared. For a pulse input, f of t is going to be something like h, and I'm going to represent that the s term here, that it happens at a certain s term minus another h that happens at s, t minus tw. And if you want to represent this in the s domain, this will be h over s into 1 minus e to the power minus t over tw. Okay, just to draw it better, t minus tw. Great. Okay, and other than that, we have, other than that pulse input, we have the sinusoidal input. So this is the sinusoidal input, and f of t is going to be something like a sine omega t, and in the s domain this will be f of s. Okay, so this will be f of s is equal to the a, of course, omega. I forgot to put omega in my PowerPoint, so that is omega over s squared plus omega squared. And if I have f of t is equal to a cosine omega t, so my f of s is going to be something like a, and that is multiplied by s squared, s over s squared plus omega squared. Okay, so these are the type of inputs that I have. Okay, these are the types of inputs that I have in my system, and if you look at the types here, these are the types of inputs. The question is, what will be my output if I have an impulse input? What will be my output if I have a step input? What will be my output if I have a ramp input? What will be my output if I have a pulse input? What will be my output if I have a sine input? And this is what we are going to see. So we are going to study the output responses depending on what? Depending on these types of inputs. Okay, so this is what we are going to do now here. And of course, just to tell you, you could have some kind of custom of inputs, in which we are going to take that in some other lecture. So you may have some kind of custom inputs. Custom of inputs, that means tailor-made. Okay, something that we cannot explain directly here. Custom inputs could be something like that. Okay, so it could be anything, like any arbitrary thing. It's not arbitrary, but it is not exactly a step or a ramp or a pulse by itself or a sine input. Okay, so this is what we have. If we have custom inputs. Now the question is that what we will have if we have this is applied. All these inputs are applied to a system. If you remember that, if we want to apply to our systems, remember that our systems that we have here, the systems could be first order, it could be second order, or it could be of a higher order. Okay, of course it could be third order, fourth order, and so on, to a higher order system. The example that we have taken, for example, from last time, that how does CA get affected by CAI, and we got a transfer function, and my transfer function was something like k over tau s plus 1, right? It was in this format, k over tau s plus 1, and we can say that this is a first order. This is a first order system. Okay, and this is an example of first order system. So what you're going to study, if we have a step input to that, CAI, and what will be my output, which is the CA. Okay, so we are studying all the types of inputs against what? Against the output. Well, we will also study the step input and the ramp input against the second order as well. Well, did we take second order? Not yet. We did not study that yet. But the transfer function of a second order will be something that looks like that. Okay, that looks like that. Okay, and did we study that? Well, we did not study that yet. So don't worry, we are going to study the second order. And how do you get the second order? An example I have taken if you have two tanks in series, and so on. Well, so we will study first order, we will study second order, and the effect of that inputs to a first order system, and the effect inputs on a second order system, and then the question is that how about the third order? What about the higher order system? So what we are going to do, the simple thing that we are going to say that we will study later how to approximate higher order to first or second order. Okay, so we are going to approximate, and this will make our life much easier. Why? Because we are simply saying that that if we study first order and second order, it's good enough for us. It's good enough. Why? Because if I have a higher order system, I always can approximate it to a first or a second order. So that is the beauty of what we can do here. Okay, so we can approximate things. So what we are going to do now, we are going to study the effect of inputs to what? To the first order system. Okay, so this is what we are going to do. And what is a first order system? If you're just going to put it as a generic format, the first order system is k over tau s plus 1. So that is a generic format of a first order system. And if this is my first order system, if I have a step input, okay, So now I have a step input. Instead of using X, I'm going to use Y, because the I'm going to use U. U is the format for inputs. It is popular to use U, and for Y, it is very popular to use that for the outputs. Okay, so consider that, for example, this is concentration over the input concentration, or the concentration over Fi. Okay, so if this was my system, and actually to make you more comfortable, if you would like, if I would say, for example, how would the concentration change if I change the input concentration? If I change the input concentration, given that it was a first order system, okay? And how is that going to appear here? Just to look at it. So this is my system here. That is my system. And what will happen, okay, let me just draw that. So what will happen to the concentration in the tank if I change CAI, okay? If I change CI from, say, 0.1, 0.1, I will say, I'm just looking for a concentration that's something that makes sense. So let me say 0.1 moles per liter, and I change that to 0.3 moles per liter. Okay, so if I change it from 0.1 to 0.3 milliliter, how would CA change? How would CA change? Okay, so that is that is a problem. Okay, that is a kind of a problem. And now I'm going to deal with it as a generic format, and then we are going to substitute. So we want to make a generic form, and then this generic form could be applied to any step input for any first order process. So in this case, what I'm going to I will try to do, I'll return back to my generic format. And returning back to the generic format, so if I have U of S, my step input, I have a step input, okay? So I'm going to apply a step input. So if I want to apply a step input, what will be my equation? It will be something like that. Y of S is equal to U multiplied by that term, so it will be M over S into K over tau S plus 1. Great. So if I have something which looks like that, M over S over K tau S plus 1, this will be, and I think so you can define this in the Laplace table, it will be Km over S into tau S plus 1. And actually this, if you go to the Laplace tables and you undergo your Laplace inverse, okay, and you do your Laplace inverse, so what I'm trying to do here, I will try to apply my Laplace inverse. So I'm going to do Laplace inverse, and doing the Laplace inverse, I'm going to find out that y of t is equal to Km into 1 minus e to the power minus t over tau. Okay, you're going to find this answer. You can do it, just go to Laplace tables, you're going to find that. And I would say that it's easier for you also to memorize, because you're going to use this this step input to a first order process very frequently. So it's good to memorize. This equation that we have here. If you want to do the math of it, to get to this stage, go ahead if you would like to do this. And the math of it says what? Says, if you can remember the partial fractionation, which is equal to A over S over B over tau S plus 1. Do you remember that? Okay, so if you do remember this, we said we are going to multiply both sides with S into tau S plus 1. So this will be like Km is equal to, this will be Km is equal to A into tau S plus 1, right, plus B into S. And then you're going to substitute where you say that if S is equal to 0, okay, so if s is equal to 0, so what I'm going to have, I'm going to have km is equal to a 0 plus 1, so that is a, plus 0, so a is equal to km, so that is my first equation. And then if I substitute s is equal to minus 1 over tau, just to cancel out the first term that you have here, so I want to cancel out the first term. So if I substitute s is equal to minus 1 over tau, the answer will be km is equal to b multiplied by minus 1 over tau. So b is equal to km tau, negative km tau. So I have b is equal to negative km tau. So if I continue with that, if I continue this part, so I'm trying to do my kind of a problem here. I'm trying to do the partial fractionating or partial decomposition. So I was going to substitute. So going to the problem here, we have km over s minus km tau over tau s plus 1. Okay, so this is the equation that I have here, and if you look at that, the first part definitely is a km, and this one is not 1 over s plus a. I can make it 1 over s plus a. How to do this? So you just divide by tau. So if you divide this by tau, so I'm going to cancel out this tau here. I'm going to cancel out this tau here, and I'm going to have a better look of my equation. I'm going to have a better look for my equation, and my equation will be km over s minus km over s plus a, and my a is here 1 over tau. And now if you take Laplace, this will be km, Laplace inverse. So that is, now I'm taking the Laplace inverse. This will be km, and that will be km e to the power minus at, right? E to the power minus at, and what's a? Is 1 over tau multiplied by t, so that will be t. Okay, so, and if you take a common factor, this will be km into 1 minus e to the power minus t over tau. I hope that you're convinced, okay? I hope that you're convinced now here. So if you are convinced now, so let's go back to our problem. So what did we say? We said that if you have a step input, to a first order process, this is what you're going to get. And if you take Laplace inverse, you're going to get this form here. Km is equal to minus t over tau, and this looks exactly like this, okay? Just to make you comfortable. So I have km into 1 minus e to the power minus t over tau. So this is the equation that we have if I have a step input, okay? Okay? And I also can study that, okay? I can study that using the initial value theorem and the final value theorem, and I can do a lot of things of analysis to know how does the output react with any change in the input, okay? And what do I mean by that? I already said step input, right? And what does the step input appear? It appears in the m value. What is the transfer function, or which describes the system? The transfer function which describes the system appears in the k, which is the sensitivity, and the response time, which tells that it is fast or low. So I have all the information of the step input and of the process within this function here. Okay, so if we would say that, what will be the value if t approaches infinity? I'm very curious about that, and I will call this y infinity. The value will be km into 1 minus e to the power minus infinity over tau, and this term will be equal to 0, so it will drop out of the term. So I will have that y infinity will be km. Okay, it will be km, and this is, it's nice to see that. All right, it's nice to see that y infinity is equal to km. Well, I don't want to go only to km. Now I know what is the new steady state value. Imagine that you know what is the new steady state value. You know, if you have a step input, what is the new steady state value? Do you know what do I mean by that? It means that if I have a response of a certain height, I will know the new steady state value of the height. Okay, how do I know that? By knowing what is the process, the sensitivity of process, and if I open the valve from 10 to 20, and I know that, from 20 to 30, so I open it from 20 to 30, that means the change is m, which is 10. So I multiply 10 with the sensitivity, I will know what will be the final value. It is that beauty. It is of that beauty I could know what is the new steady state value, or the y infinity here, right? Y infinity is like the new steady state value. Well, let me calculate things in a different way. Let me do some kind of substitution and see how it goes. Okay, and what I will try to do here, I want to see what will be the value of y, okay, at different time. So I will not only look at time is equal to infinity, I will look at the value of y at different times. And here, what should I substitute for time? I'm going to substitute for time for tau, okay? So why? Because I cannot say 1 and 2, because tau is unknown. If it is known, I can substitute 1, 2, 3, okay? Usually tau is not unknown, but if it is unknown, then I will have a problem of substitution. So what I'm going to substitute here, I'm going to substitute 1 tau. Let me say that before 1 tau, I'm going to substitute for 0 tau, and then 1 tau, and then 2 taus, and then 3 tau, and then 4 tau, and then 5 tau, and so on. So I'm going to start to substitute. And in substituting, I already have my equation here. If you can look at this equation. So this is my equation here. Okay, so this is my equation. Y of t is equal to km to 1 minus t over tau. So if you substitute for 1 tau, this will be, for 0, so this will be e to the power minus 0. And what is e to the power minus 0? Anything to the power 0 is 1. Okay, and that will be 1 minus 1, which is 0. So at time 0, y is 0. It makes sense, of course. Nothing happened, y did not change, right? Okay, for t is equal to tau. What will be the answer? It will be 1 minus e to the power minus 1. And what is 1 minus e to the power minus 1? I already have the values, and I can show you the values in this slide. So you can see that at 1 tau, 1 minus e to the power minus 1. Okay, so that is 1 minus e to the power minus 1. What is the answer? It is 0.632. Okay, and so we'll go back and write that is 0.632. And actually it is 0.632 km. Okay, so what we are trying to say, at one time constant, I am reaching 63.2% of km. I'm reaching 63.2% of km. And this is applicable if I have what? A step input to a first order process. So at 1 tau, I'm reaching 63.2% of km. 60.2% of km. And what is km? It's y infinity, the new steady state. Okay, so I'm reaching 63.2% of the new steady state. And what is the value at 2 tau? It will be 0.865 km. If I can remember that, yes. What is 3 tau? 0.95. So I'm just copying that. It's 0.95 km. And here it is 0.982 km at 4 tau. And for 5 tau is 0.993 km. And that is good enough. I don't want to substitute more than that. There are 2 things that I want to mention here, okay, from what I have done. because we try to study the system, and out of what we have studied, we try to come up with some generalizations, with some kind of judgments that we can use in future. The two things that I need to mention here is that definitely at 1 tau I'm going to reach 63.2% of Km. In other words, if I want to find the time constant of my process, I can take the 63.2% of the Km, or from the initial to the final value, I take the 63.2% and I can find what? I can find tau. So I can do it the other way around. From the 63.2% information, I can get the value of tau. So for example, I have a tank. And within that tank, I open this Fi from 20 to 30%, and because of that, my tank changed from 3 to 3.2. Okay, so what is the change? It changed from 3 to 3.2. So the change is 0.2. The change is 0.2. If I multiply 63.2% to 0.2, I can find what? I can find the value of tau. And that's the beauty of it. I can find the value of tau just by what? Just by knowing some information about what? About my system here. And we are going to take an example. So hold on if you didn't understand that example, because we are going to take it later as well. So that is a very good information that I need. The second good information that I want to obtain here for my process is, the second good information is that at 5 tau, it's like I'm reaching my new steady state. My new steady state value. Because I'm reaching 99% of Km, right? My new steady state value, which is 99.3% of Km. And that is the other information that I would like to use within my problem here. So what do I have? I can reach my new steady state value at 5 tau. So if I have a process, for example, my process of, just an example, that I have the temperature, I'll write that in white. So the temperature will change because of the change of my input temperature, or the change of the coil temperature. Okay, change of the coil temperature. So I'm saying that if temperature changes, if there's a change in the coil temperature, I change the coil temperature from 20 degrees till 30 degrees. Okay, so if I do this change here, and this is my system, for example, this is my system showing that this is 1 over 10 seconds s plus 1. So what information I can get from here? If I know that 10 is equal to 10 seconds, I definitely know that if I have a step input in TC, it will take 50 seconds for my system to reach what? To reach to the new steady state value. So if you are a supervisor, if you are a superintendent sitting in an industry, and you know that the time constant is 10 seconds, and you told the operator, please, you told the operator that it will take 50 seconds or about a minute to get to the new steady state value. And then the operator waits for the response, and he discovers, well, that it takes about 50 seconds to reach to the steady state value, and says, wow, how did you know that? You're still new in the industry. You don't have this experience. Where did I get the information from? I can get it from the transfer function. I can get that from the transfer function. And that is the beauty of it. So what we have done so far, we have taken a step input to a first order process, and from the step input to the first order process, I'm getting I obtained my form. If I have step input m over s to a first order process k over tau s plus 1, this is my shape in this, how it looks like, in the S domain. And if I want to see how it looks in the time domain, I can do the partial fractionation or partial decomposition, but I'm telling you, you don't need to show this to me in the exam. Okay, so what you need to do, you can just go directly and show that y of t is equal to km to 1 minus e to the power minus t over tau, which is part of doing the partial decomposition and taking the Laplace inverse. And then we have calculated y at different values. So we have calculated how what is the value of y. We know y infinity is equal to km, but we said that we want to calculate at different values of 0, tau, 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. And we have discovered that at 1 tau we will reach 63.2% of the change, which is km, okay, which is km, the change, which means the new steady state minus the old steady state. And within 5 tau, I'm going to definitely reach very close to my new steady state value. And these are two good information that we have for a step input to a first order process. Okay, great. So what do we have for from our step input again? So I'm just going to show you something that we already have done, but I'm going to show you in terms of initial value theorem and the final value theorem. What is my system? So my system that I have, y of s over x of s is equal to k over tau s plus 1. And in substituting, I have a step input, so this will be km, as we said, km. This is m over s, so I will do it step by step again. So this is m over s, that's the input, into k over tau s plus 1, and this will be km over s over tau s plus 1. Okay, what does the initial value theorem say? The initial value theorem tells me that to find out for t approaches 0, that initially what it was the value for y of t, I can directly say that using initial value theorem, I substitute for s approaches infinity. However, I'm going to multiply the transfer function or the y of s into s. And if I multiply this by s to my function here, okay, so this is y of s, I will have s multiplied by km over s into tau s plus 1, cancel out, and if I substitute for s is equal to infinity, so it will be infinity plus 1 infinity, and any value over infinity will be equal to 0. And actually this is exactly what we have said. When we substituted t is equal to 0, we find that y is equal to 0. Okay, so we are getting the same result. That is what I'm trying to say here. And considering the final value theorem, the final value theorem says that I want to find what is the value of y of t, my output, if t approaches infinity. And this means if s approaches 0, this is the final value theorem, okay, which substitute s approaches 0, I'm multiplying by the y of s with s. So when s approaches 0, for the same function, s multiplied by that function here, cancel out. If I substitute for s is equal to 0, I will have 0 plus 1, which is 1. So km over 1, which is km. So I'm getting the same answer for the final value theorem, that y infinity is equal to what? Y infinity is equal to km. So I'm getting the same answer, but I'm just showing that to you so that you get more comfortable with the initial value theorem and the final value theorem. So that is for the step input, for a step input to a first order process. For a step input to a first order process. Beautiful. So that is the first part that we have taken for the type of input, which is a first order process. What about if I have an impulse input? I just forgot that, okay? If I have an impulse input. What about if I have an impulse input? Okay, if I have an impulse input. And this impulse input, where the Dirac function, if I take that Dirac function into the S domain, it will be 1, and this is what we have said. So if I have a generic system, again y of s over u of s, which is a first order process, and I want to substitute the input as 1. So my input is an impulse input, so u of s is equal to 1, so I'm talking about us is equal to 1. And if I substitute that, this will be y of s, which is equal to 1 multiply k over tau s plus 1. So I'm going to get the same question here. Oh, and if I just want to represent this in a format so that I can take the Laplace inverse, I will have this plus a. So I'll divide by tau, so to be k over tau over s plus 1 over tau. And this is like 1 over s plus a. And the answer here will be, after taking the Laplace inverse, it will be k over tau, okay, that's the constant value, into e to the power minus a t, which is 1 over tau into t, so that will be t over tau. So that will be the function of what we have for an impulse input. And again, that is the answer for y of t. So y of t is equal to k over tau e to the power minus t over tau. So this is what I'm going to have, and this response will look something like k over tau to e to the power minus t over tau, something like that. Like it was something up there, and it will reduce down. It's e to the power minus t over tau, right? So it will reduce down to 0. It will reduce down to 0. I need to go a little lower here. So it's like starting from a certain point, and from a certain point at 0, and then it returns back to its initial point again. So it's returning back to its initial point. Okay, so this is what I have here in my process, and it's very clear that my impulse function decays with time. So the impulse function is very clear that it had an effect, and the effect went away. So the impulse function decays with time. Its effect, okay, impulse function effect decays with time, and it's very clear that the decay goes back to 0. Okay, especially that you're talking about deviation, so the decay goes back to 0. And when you say the decay goes back to 0, here we are talking about the deviation. Okay, so it's like it was at a certain steady state value, which is steady state minus steady state 0. So it was at a value where there's no change, and then there was a change, and then it returned to its original place where there was no change. Okay, so that's what it means. So this is what we have for if we have a impulse input to a first order process. What about if we have now a ramp input to a first order process? Okay, so if we have a ramp input to a first order process. If we have a ramp input to first order process, again we are going to start with our generic format of a first order process. And if we say that we have a ramp input means, okay, a ramp input means my u of t is equal to at, and this means that my u of s is equal to a over s squared. And if I substitute that, this will be y over s, ys is equal to a over s squared multiplied by k over tau s plus 1. And now there's more math to do here, and you need to do partial fractionation. Definitely you need to do something like that, partial fractionation, a over s plus b over s squared plus c over tau s plus 1, and you're going to find the values of a, b, and c. And we can see that there's a term where there's a constant, and there's a term where there's a t, and there's a term where there's an exponential term. So I can see that the answer here, how it will look like. So just to make things easier, and you just need to go to do the math. Okay, so what do I have here? I'm going to have a ramp input, that is AT, and this will be A over S squared, and rearranging, of course, is just rearranging it, multiplying the first order, which is K over tau S plus 1, and multiplying by A over S squared. And if you do the partial fractionation and the partial fraction expansion, and then you take Laplace inverse, this is the answer that you're going to get, okay? Which is Ka tau into e to the power minus e over t over tau minus 1 plus Kat. And as we said, you're going to have a constant term, which is Ka tau. You're going to have the ramp term, which is Kat, and you're going to have the exponential term. So if you want to look at that, you see this is the constant term, okay? This is the constant term, and this is the term which we have a ramp, the t term, okay, which is Kat, and this is the term which has the exponential term. So we can see that you can do your math and find out that. So my y of t, okay, my y of t is going to be equal to, okay, it's going to be equal to Ka tau into e to the power minus t over tau minus 1 plus Kt. Okay, so this is what we have here. This is what we have as a function here, and looking at what we can gain from that information here, this is the response, how it will look like. So if this was my ramp input, my output will look like that. Okay, my output will look like that, and then it will be like a ramp input which looks like that, and the distance between these two will be tau, which will always be tau. In other words, what will happen as t increases, my exponential term is decaying. Okay, as t increases, my exponential term is decaying, and we know that this exponential term will be decaying till some value. If we get approaching to 5 tau, this will be e to the power minus 5, which will be a very small value. Okay, so that is the answer that in your head. So if I go to higher taus, okay, if I go to higher taus of greater than 5 tau is enough, I'm going to have this term decaying. And if I have it decaying, if I have this decaying and going to 0, my equation will be reduced to Ka tau into 0 minus 1, so that is minus, plus Kat. Okay, and this will be an equation which looks like that: Ka multiplied by, as a common factor, into t minus tau. Okay, so the difference is what? Is tau. You just can see that from the equation here, that the difference is tau. And this is why what we have tau here. Okay, why I'm telling you this? Because in the exam, I could give you a figure which looks like that. And of course, I will hide this term. I'm not going to say what is that. And no as and nothing at all. So I'm going to tell you there was a ramp input for a first order process, and this is what we obtained. And then you're going to tell me, Professor, okay, you didn't give us the value of tau. Doctor, you didn't give us the value of tau. Please give us the value of tau. And then I will tell you, well, it is in the figure. Go find it out. Of course, I'll not tell you it is in the figure. I'll tell you, sort it out. And then you're going to be stuck. And just to tell you, this was part of many exams that we had in past exams. And many students do miss it. So this is tau, okay? This is tau. Don't get it from here. That is not tau. It is when t is really high and the exponential term is decaying, you can get the value of tau. Where? When you have the exponential term is decaying. And the exponential term is decaying. A very good place that you can measure is about 5 tau. Okay, is about 5 tau. So this is what you need to know for this is what you need to know. This is what you need to know for the ramp input. So that is a ramp input to a first order process. Now, what we will have if we have a sinusoidal input for a first order process. So we have taken what? We have taken impulse, step, a ramp input, and now is the sinusoidal input. For a sinusoidal input, my u of s is going to be a omega over s squared plus omega squared. And if we have something like that, which could be a variation in cooling water temperature, or it could be a noise, electrical noise that is disturbing your system, how will your reaction, how will your output look like? So in the sense, I'm having y of s over u of s over, which is k over tau s plus 1. And let me write that in the other side of my board. Okay, so now I'm talking about if you have a sinusoidal input to a first order process, and again, you already have seen that many of our processes are all is first order. So it is good to study to a first order process. So if you have y of s over u of s is equal to k over tau s plus 1, and if you say that u of t is equal to a sine omega t, which means that u of s is equal to a into omega over sine s squared plus omega squared. So that is u of s. You're going to substitute u of s and y of s, and y of s is going to be equal to a omega over s squared plus omega squared into k over tau s plus 1. Now, what you need to do, you need to work on the partial fraction expansion on that. And this will take some kind of an effort, and I saved this effort by going back to the PowerPoint slide, and if you have u of s as a omega over s squared plus omega squared, you multiply it with the first order, and after doing the partial fraction, you can see the partial fraction that you are trying to do here. After you do your partial fraction and you get the values of the partial fraction, which is a, b, c, or alpha naught, alpha 1, alpha 2, you're going to get, and after you do the Laplace inverse, which is inverting, you're going to get this y of t. So this is y of t. So what we can gain from y of t? Of course, I'm not asking you to memorize this, okay? But there are several information we can get here. First thing, it's written there that this term dies for large t. Very similar to what we had done for the ramp input. This will die at large t. At a large t, what we will have? We will have this term only. And what does that mean? It means that my output will have a phase shift from my initial input. So what does that mean? My initial input was just a sine omega t, right? Which means if I had a certain frequency of omega, so I have a certain frequency of omega, and I think so I'm going to well, let me continue, and I'll try to draw it later on the whiteboard or the blackboard. It will be easier. So if I have, well, let me write. Let me go to the whiteboard. I think so it will be easier to do that. So what I'm trying to say that if you have your input, as, and let me do that in white. If you have your input as a sine omega t, okay, so that's my input, and my output is some kind of a long one. I can't remember it now. Oh my god. Okay, so and I have my output which looks like something like at large. Of course, I'm going to take at large t, so I'm going to drop out this term. So I'm going to use this term only, which is Ka over over omega squared tau squared plus 1, so that is Ka over omega squared tau squared plus 1, and that is multiplied by sine omega t plus phi. So what do we have here? What do we have here? I just want to mention that now in my figure, that is my figure here, my input, okay, my input, which has a certain frequency, it will go like that. Okay, it will go like that. And that is like my input. Okay, it's not as beautiful I would expect, but please, I'm trying my best to draw my figure here. And for the output, it will have a phase shift. Phase shift means what? Means that it's starting at a different position. And it's not only that it is starting at a different position of phi, it's not only that, actually, it also means that it has a different amplitude. The amplitude here is A, so this is like A amplitude. And actually I should have drawn this with the blue one. Okay, so this is A. And the amplitude of the second part, here, the amplitude multiplied by sine, the amplitude is different. It's a different value. It's A divided by, it's multiplied by K and divided by K omega squared tau squared plus 1 under the square root. So what I'm trying to say that this will have a phase shift, and in addition it will have a different amplitude, okay, a different amplitude, and it will be something like that. I'm just drawing it as much as I can. So I'm going to have a different amplitude and I'm going to have a phase shift, okay? So I'm going to have a different amplitude for my output and I will have a phase shift, okay? So this is for my y of t, the output. So going back to my problem, and this is what it shows. It shows that my A, and this is my system, and I think so it's a good idea that I draw this here, and I'm not sure that if I'm really good at it. Okay, so if this was my input here, I'm going to draw it again. Okay, just faster, it becomes better. Okay, so this is my input, and what is my output? My output has a different amplitude. Okay, so you can see the different amplitude, and it started with a shift here. Okay, it started with a shift here, and this is what you really need to know about this so far. And we are going to get we are not going to study into the depth of the sinusoidal input. We're just going to go to what is more frequently happening in the industries. Okay, so as a summary for the sine input, we just say that it will have a different amplitude and it will have a phase shift. So this is what we have, and I can calculate the amplitude ratio of the input to the output, which will look something like that. And definitely it will have a phase shift of phi, which is minus tan inverse omega tau. Okay, so all that can be calculated. Okay, there are some kind of other systems that we could consider, but I'll come to this process to sometime later, because we want to study the integration process. Because before I come to this system here, because we are talking about only first order systems, right? This is a different process. Actually, I explained that there's a first order, there's a second order process. There are also some kind of an integrating processes, right? So I did not explain that. So other than having first order and second order and the third order and a higher order, the ones that I have showed to you at the top here. Okay, where is that? Okay, so we mentioned that we have impulse, step, ramp, pulse, sine. So these are all kind of inputs, and we applied this to what? We applied this to a first order. We did not do that for a second order. However, I also need to mention that it also could be applied to an integrating process. and I don't know why I said that in red. I don't think so. It's a good idea. We need to put it in white. Very similarly, so we can also apply this to an integrating process, and we'll take this, of course, in another time, in another lecture. Okay, so can we sum up? Okay, sum up all what we have done to sum up out this lecture. Yes, we are going to sum it up, and by summing it up, I need to write the equations. I would like to write the equations again here, and just bear with me till I get to the bottom of that blackboard. So what do I have here? If you can remember, I have an impulse input, and my impulse input in the time domain, okay, in my time domain it was like a Dirac function, and then in the transfer function or the S domain it was the value of 1. Okay, and this impulse input was applied to a first order process. So I'm talking here this table that I'm looking at is an application to a first order process. So I need to write this here. So this is an application to a first order process, which is something like k over tau s plus 1. Okay, so this is what I'm looking at. And if I have my impulse input, which looks like a Dirac function in the S domain, and I multiply this, I'm going to get my y of s. My y of s is going to be something like k over tau s plus 1, the same. And if I find the y of t, it will be k into e to the power minus t over tau, k over tau into e to the power minus t over tau. Okay, and I'm going to have some kind of, I'm going to make that a little smaller because I'm trying to summarize everything that I have. And how does my input look like? My input will look like, if I just put my u of t response, my input response will look like something like that. Okay, I think I need to draw this better. So it will go up and then it will turn to exactly same value here. And my output response, it's like it will get affected to some point here, but it will decay like that. Okay, so it will decay as we can see here for our output. So this is the output response. Okay, so this is my output response. And if we go for a step input, okay, so I have my step input. My step input looks in the time domain as m, and in the S domain it will be m over s. And if I multiply that, it will be something like that, km over tau s plus 1. When I found y of t, the answer was km into 1 minus e to the power minus t over tau. What was the shape of my input? My input was something like that. It goes from a certain value to m, so this is m, and my output looked something like that. Okay, something like that, going to a new steady state. And just to consider that if I had a step input which is negative, okay, my output will be something like that. So don't worry, it will get to a new steady state value. Okay, and it will get to a new steady state value here. So this is like, instead of m, I'm going to say it's like minus m, right? Okay, so don't get confused with that. So this is how it looks like. Now that's the step input. Now if I have a ramp input, my ramp input will look something like at in the time domain. In the S domain it will be a over s squared. And if I multiply this, this will be like k a over s squared multiplied by tau s plus 1. And then I found out in the time domain it will look something like that, which is k a tau into e to the power minus t over tau minus 1 plus kat. Okay, so that was the output. I know that I just got crowded with what I have here, and my input was something like that. My input, like nothing changing, and then there was a change. And my output, and I'm just drawing here my input with the output because it just looks better when I draw them together. So if this was my input, so my output will be something like that. Okay, so it's going to be something like that and like that. Okay, and the difference, if you take it at 5 tau, even lower, sometimes you're going to find the value of tau here, right? So this is what we have here. And finally, for a sinusoidal input, which looks like a sine omega t. Okay, so this is a sine omega t. And in the S domain is going to be looking something like a omega over s squared plus omega squared. And if you multiply that, this will be k a over s squared plus omega squared into tau s plus 1. And my input, and I'm going to draw that input, which looks something like that. Okay, I don't know if this is good drawing. Okay, it just gets more difficult when it gets smaller. So if I just want to draw this, I'll do my best. Okay, oh my god, again that's not good. How to make it good? Okay, I need to fix my hands. Okay, so it will be something like that. Beautiful. Okay, and this doesn't change, the height is still the same. Okay, the height is still the same. And if I'll take that as an output, so now again what I'm trying to do here, just to show my input. So if my input was something like that, my output is going to be something like that, with a different phase shift and a different amplitude. Okay, with a different phase shift and a different amplitude. And different amplitude means that it's also going to go lower here. Okay, it's like that. Okay, I hopefully that just clears up the thing. So these are the type of inputs and its effect on the output. So what we have taken the effect of different inputs, the effect of the different inputs on a first order process, and I hope that we are about to finish chapter 4, and what we are going to take next time, we are going to take, if we are going to have this effect of different inputs, and we are going to concentrate only on the step input for a second order process, and we are also going to take the integrating process. So we are going to look at these kind of processes, and by that we are going to take the third part, which is the custom input to a first order process, and we are also going to take it only for a first order process. And by that I think we have a good picture of what we are trying to look at here for chapter number 4, looking at different types of inputs for a first order process. Why we are studying first order process, as you have seen from last time, all the transfer functions that we have obtained look like a first order process. So definitely a first order process is important. There are second order processes, yes there are, and we are going to study the effect of those inputs on a second order process. However, we are going to only study the step input to a second order process for the sake of the time and the limitations that we have in this course. By that, thank you very much. We had done a very great job here, and I would like to use a bigger, yes, that looks even better and better. Okay, yes, that's a very happy smiley face. I think it's a crazy face. Okay, so see you, take care, and we have done a good job today. Thank you very much. Take care. Ma salama.